So we are very glad to have Professor Whittaker here to talk about why software fails. And this is going to be the shortest introduction I've ever done because I'll let him self-introduce. Thank you.
Let's see, you must have heard that I was going to be breaking software, so that must explain the large crowd. I appreciate you coming. As he said, my name is James Whittaker. I'm an associate professor of computer science. Is this working? Okay, you can hear. I'm an associate professor of computer science at Florida Tech. And there's other introductory stuff that you're not interested in, so I'm going to skip it and get to the talk. This presentation sort of came about innocently, this body of research I'm going to be telling you about. Last October, I was teaching a class, a software engineering class. Actually, I shouldn't say software engineering because I actually teach people how to code in my software engineering classes, which is fairly unique, I understand. So let's say software development class, and I was writing a program on the board, and I was teaching my students how to write software that doesn't fail. And I looked up at the board, and I saw a bug in my code. And I looked down at my notes. It's hard to write code on the board in front of a bunch of people who are poking at it. And I looked at my notes, and I saw a bug in my notes. And I thought, this is a bad sign. So I had all the students say, okay, there's a bug in this program. Find it. None of them could find it. And I realized, I've been teaching from this same little program for about 2 years. And Florida Tech is on the Space Coast in Florida. We're just south of NASA. There are 10,000 software developers in our county. Extremely high-tech area. And these people come to my classes all the time. They're much better programmers than I am. And they didn't find the bug either. For years I've been working with this buggy program. And so I got to thinking about it and realized that, this bug is... Sorry, I got this growing audience. I'll try my best to stand where you see. I thought this bug is typical of other bugs. And so based on that theory, I went out and started breaking other pieces of software and realized I'm onto something. Yes, it's on. The audience isn't complaining.
I'm sorry.
I'd release ready by professional testers and developers and break them. It's on. It came on with the word break. I like that. And so that was the assignment. They had 2 days to complete the assignment, and so they all went out and they broke software. They broke Microsoft software. They broke Sun software. They broke all kinds of software. All 26 students succeeded. They all found bugs. Actually, that's a lie. There were really 35 students, I think, in the class, and the other ones dropped. But 26 students succeeded.
And so now we feel we're onto something here. And since January, we've broken literally hundreds of software applications. We have yet to not break a software application. We did receive a challenge from Cisco that you can't break a router. And so we found a TCP packet that broke the router. And they said, well, that's not fair. TCP's too big. You can't break the router with ARP, Address Resolution Protocol, the simplest type of packet that you can possibly apply. And a student of mine locked up every router on our campus with one single ARP packet. And so this is the setup. This is what I'm going to talk about today with this little methodology that we apply. And the campus wasn't too happy with us. They found some MP3 files on our hard drive, and now they're trying to. They hate us so much they're trying to get the FBI in for us pirating music software. But anyhow, this is a battle we're willing to fight. So that's what I'm going to talk about today. I'm going to introduce it, though, by talking briefly about the other solutions that people have posed in the past to the software quality problem. And then I'm going to pose my testing solution. So the first solution to the software quality problem came about in the 1970s by the formal methods and mathematics community. The plea went, if only you work more formally, your software will be better. And some really good ideas came out from that. Structured programming, object-oriented programming, both had their birth from formal methods. But in general, I can describe formal methods as a treatment of programs as a math problem. Writing a program is like, proving a theorem. And it's a nice idea, and I was trained, my advisor is a formal methods person, and I apply formal methods regularly. It's a lot of fun. But in the 20 or 30 years that we've been applying formal methods, we have yet to scale it up to real programs. We can only work with very small, very simple programs with formal methods. So this can't be the answer to the problem that software is too buggy. And certainly we haven't been able to find developers who will do these sorts of things. This is sort of the reaction we get from developers from formal methods. That's my picture of a developer, a sumo wrestler in underwear. That's the best thing I could come up with. The 1980s brought the tool vendors to solve this problem. They thought, if only you work with the right tools, namely the ones I'm selling, your code will be better. And the industry bought it. We bought thousands of tools, spent billions of dollars on CASE. That was the word of the 80s. Computer-aided software engineering. And it's all shelfware now. What do developers use? They use a text editor, they use a compiler, they use a debugger. They don't use fancy CASE tools. They don't draw fancy pictures. They build tables. Specifications are written in Word or Emacs. And programs are written in Emacs and are compiled and debugged. The tool vendors failed us as well. They're all sitting in the Bahamas now on the beach, I think, with the money. And so developers had essentially the same sort of attitude about tools as they had about formal methods. And then the 1990s came along. And these people are my worst enemies, the process people. And their idea was, if only you work more carefully, if only you allow us to micromanage you, your code will be better. And so now the 90s are almost over, and our managers are busier than our developers, and our code is still lousy. So once again, the technology that has come from academia and from industry has largely failed. Now, I don't want to be too hard. There are a lot of good ideas. You should work carefully. You should have a decent process. But that's a management solution to what is largely a technical problem. Code quality, writing code, testing code is a technical problem, and it demands a technical solution. Now, in trying to face this problem as a researcher, I wanted a good approach. And my approach is a testing approach. If we can't figure this out, if the development community hasn't figured this out, if the process community hasn't figured this out, and the tool vendors haven't figured this out, what can I do as a tester? Well, I need data. So I'm going to go out and break a lot of software. I'm going to break every piece of software I can find, and perhaps I'll learn something. Perhaps there'll be some patterns that will emerge that will make sense. And I can catalog these patterns. And then once I find the pattern, I can teach someone else the methodology, and they can go out and break software until the realization finally hits that there's a solution to this. There's a way to code around this. There's a way to write our software so that this class of bugs won't creep into the process. How do we do requirements analysis and design that will keep these bugs out? So this is a testing approach, and that will eventually lead to a development solution, I hope. It's a long-term problem, but it's one that's been a great challenge to us and a great deal of fun. And I hope you'll enjoy what you see, which is, first of all, we've got to get the developer to knock this process slide out of our way. There we go. And we'll continue with the rest of the talk. We need a fourth proposal. And my proposal is that I don't know how to solve this problem either. I'm no better than the rest of those guys, but my approach is from a testing standpoint. I'm going to break stuff. I'm going to keep a big database of bugs. I'm going to try to find out how these bugs are creeping into the process, and I'm going to make better. I'm going to hopefully make testers better at exploiting bugs and developers better at preventing bugs as a result. Now, the way I'm going to pursue this in this talk is I'm going to show you how to break some software. I'm going to show you some bugs, and I'm going to talk about the ramifications of these bugs, and then I'm going to generalize them into our theory. Once I show you the theory, then I'm going to show you some more bugs that demonstrate each of the four classes of faults that we've been able to find so far. Okay, so let's break some things. Now, I'm going to break Microsoft products because I'm at Microsoft. I'm not picking on you all. I like you all. If I didn't like you, I wouldn't break your software for you. So this is a simple bug. Now, the first bug I found when I was working on the board was a problem that came about because I was doing math. And so the first product we worked on was the calculator for all three of the Windows platforms that we had, 95, 98, and NT. And it turns out, by the way, you have to, when you reproduce these in your desk, make sure you try all three of those operating systems because the calculator fails differently on each of the three. Now, this is the first example I'm going to do. I'm going to take 1 and I'm going to raise it to a very large number. Now, that's 1 times 1 times 1 times 1 is still 1. The answer is 1, right? So this is a fairly simple calculation. We should be able to expect the right answer. But the bug, obviously, we're not going to get 1. I think you're on to me. But the results of this bug are extremely interesting, and they point at something that developers are trying to use to prevent bugs that doesn't work. So let's go ahead and do this. I'm going to enter 10, and I'm going to raise it to 31st power, and I'm going to store that number in memory. Then I'm going to clear the calculator, and I'm going to take 1 and raise it to the power I have in memory, hit the equal sign, and I caught an exception. It says an unknown error has occurred. Now, that might be reasonable behavior. That is a fairly big number. So the person who wrote the calculator might not want to deal with those big numbers. It doesn't look like that was the logic. It looked like, something bad might happen here, and so I'll write this exception, and the operating system or the runtime library will catch it, and I'll be fine. Now, whenever a tester sees this situation, we get a big smile on our face because we know the developer didn't really know what they were doing here, or we would have had an error message that made a little bit more sense. So you're sitting at your keyboard and you get a big smile on your face and you think it's just a matter of time, just a matter of time. And testers are usually right. Now what I'm going to do, I'm going to say, okay, unknown error. This calculator is mine. I'm going to clear it out. Doesn't help. And I'm going to repeat the exact same operation. 1 raised to the power 10 to the 31st. And now I overflow memory. Now this is interesting. 1 raised to the power 10 to the 31st. The first time tripped the exception. The second time the exact same sequence of operations, the exact same inputs, cause a different error message. Why? See, this is what's so interesting from a research perspective. What could possibly be different that the same input gives me 2 different results? Well, only one possible thing. This software was in a different state the second time than it was the first time. Tripping that exception corrupted state. Exceptions don't work. Whenever a software tester trips an exception, that's it. That software has lost state, and it's just a matter of time until you're able to kill it. And this demonstrates that particular error very nicely. But this is important data. This is the type of analysis we try to do in order to understand what's really going on under the covers. All right, let's break it again. This time, this is a great bug. If a big number is acceptable to the calculator, shouldn't half of that number also be acceptable to the calculator? Isn't that reasonable? Now, that's not fair. I'm being hard here. I would like to say that the person who wrote this calculator is a better coder than I am, just in case you happen to be in his room. I want to make that perfectly clear. I'm trying to learn here. I'm not trying to make fun of anyone. I'm going to trick this calculator. There is a number, the biggest number that one can enter. The problem is, I can compute a number that's even bigger than that. So let's go after this one. I'm going to enter 308, and I'm going to take the inverse log. So log makes numbers bigger. Smaller, much smaller. Inverse log makes numbers much bigger. So now I got a huge number. Divide it by 2, and the result is too large. Isn't that wonderful? So we've got this disconnect between what the developer is allowing into the system as input and what the developer is allowing you to calculate and then store. So there's a disconnect between calculations and inputs. Really, really bad idea. And obviously we can exploit this to get a very strange result. How about another one? Okay, now this is a nice one. Square root of 2. And then I'm going to square that twice. So I take the square root of 2, raise it to the 4th power. That's like taking the square root of 2. And then when I square it again, I get 2 back. Square it again, I get 4. Right? Let's see. The analysis of this bug is interesting. So I have to take the inverse x squared to get the square root because there's not a square root on the calculator. Raise it to the 4th power. Hey, I got the right answer. What happened? Well, it got the right answer, sort of. What's 4 minus 4? Let's see if it got the right answer. It tells me the answer is 4. Let's subtract 4, and I get 0. Well, I got close to 0. Now, this number, I submitted this to the developer, and the developer told me that is within 32 bits of precision. It's close enough. It matches spec. And the developer's right. This is an overflow-underflow problem, and the developer's absolutely right. I probably wouldn't have fixed this either. But I think the explanation of this bug is much more subtle than that. The problem is the developer displayed 4 to me. The developer was keeping the tree of operations. And the developer wasn't just calculating and allowing underflow or overflow to hurt him or her downstream. The developer actually looked back and said, okay, this number, it's close to 4. It's actually got a result slightly larger than 4. Is 4. Displayed 4. But didn't store it. They stored something else. They stored the precision, where they dropped precision. They stored that, displayed something else. That's a dangerous situation. Now the user thinks they're working with an integer, but there's really some floating point number that's actually stored that has dropped precision. So there's a disconnect between the display, between the output, and stored data. So the prior bugs I've talked about the disconnect between inputs and the results of computation. Now we've got a disconnect between outputs and stored data. It's another dangerous situation. So the precision isn't the problem here. It's storage and output that are the problem. Yes, sir?
Question. Were you able to do something like this for an electronic calculator that you hold in your hand?
They have different sets of bugs. But yes, we can break electronic calculators too. They have software. There's one particular calculator made by Hewlett-Packard that was the hardest one to break. But we eventually overflowed and underflowed it into similar situations as well. Good question. Okay, here's another example. I'm gonna break left shift now. Left shift, LSH, works on binary numbers, and so it takes 2 operands. It takes a binary number, and you hit left shift, and then you give it an integer to tell you how far you want to shift. Now I'm gonna break both of those operands. I'm going to give it illegal values for both of the operands. First of all, instead of a binary number, I'm going to give it a real number. And I'm going to leave the second operand blank. I'm not going to tell it how far I want to shift. So let's do this one. Now this is just a large random integer, and I'm going to exponentiate it to make it a real number. And left shift equal. This is good. It says, and maybe they're right, this operation is going to take a very long time. The bug here, first of all, they didn't filter the input. They should have filtered that input and not made this computation. It's an illegal computation. But this is great. It says, do you want to continue? If you push stop, it stops. Not the operation, the application stops. This application is hung. It will not operate. You have to go to the task manager and shut it down. So, when they said stop, they really meant stop. Forgot to filter inputs. One more, and then I'll tell you my secret. And be prepared for something that's very intuitive. Okay, here's something simple. You take a decimal number, convert it to binary, and back to decimal, and you get what you started with, right? So let's do this. Let's do -2. Now I looked this up. This is working on 2's complement numbers, and that is the binary representation of -2 and 2's complement. All those ones at the front, that's the representation of a negative number in 2's complement. So far so good. Convert it to decimal, and that's not the decimal representation of -2. That's actually a very large positive number. This was a strange bug. Of the 3 operating systems we tried it on, 2 operating systems got it right, 1 operating system got it wrong. What's going on in the environment of this calculator that caused... Is this a bug in the application or a bug in the operating system? I'm not sure, but it's a compelling result that only 1 of the 3 operating systems botched this and the other 2 got it right. I'd love to have the source code of all 3 of those in order to be able to diagnose this bug further. But it's certainly, we have some indication that either you all have a horrible regression testing problem, or there's something in the environment that's causing this problem that I don't have access to. One of those 2 possibilities. Now, we did this... Yes, question? I'm not sure, but I can look at my notes later and tell you. I believe it was 98 that had it wrong. Now, we started off with 95, and we found a list of bugs. We submitted them to Microsoft. They couldn't reproduce them. They were working on Windows 98, and we thought, okay, so they fixed them. So we went to 98. We found bugs in 98 that were fixed in 95. Then we went to NT, and it had a completely different set of bugs, although it was closest to the 95 bugs. And so we're, by the way, all those product areas, they're better developers than I am too. Now, what's going on here? And why is the software so easy to break? This is software that's certified release ready. Maybe by program managers, not by the testers, certainly. But there's something simple that's going on here, and we've come up with a very simple recipe, very simple theory about why software fails. And the theory works in the sense that we can teach someone who's never tested software in their life, a student at my university, and sick them on software, and within a few minutes they can use this recipe to bring the software down. And so let's talk about why software fails. There are 4 reasons that we have currently, although we had 3 for quite some time. Finally, we found a bug that couldn't be explained by the first 3 reasons, and so we had to create a 4th category. I am willing to admit that there may be a 5th category or a 6th category. I don't know what it is yet. Every bug we've been able to find in all the software we've tested fits nicely into one of these 4 categories. Software fails because the developer's improperly constrained input, improperly constrained output, improperly constrained stored data, and improperly constrained computation. Now that is about as simple as it gets, about as intuitive as it gets. What does software do? It accepts inputs, produces outputs, stores data in data structures, and computes stuff. That's it. So the fact that this hasn't been published before absolutely amazes me. That such a simple theory could elude us for so long, or maybe it's common sense and we all assume that it's correct, but we've never exploited it. this gives us a systematic way of breaking software. The first thing you do, you go after the places that inputs enter into the system, and you pound on those. The second thing you do is you look at where outputs exit the system, and you try to get the wrong output to come out. You try to get an output that won't be processed by the environment. So it's like looking from the inside out, and inputs are like looking from the outside in. And you try to come up with scenarios that break it. Stored data. If you can't break it by input or output constraints, which is generally not the case, we can usually break software by all four of these areas, you look for data structures, arrays, any type of data structure, and you try to underflow them, overflow them, or get them to store value that they shouldn't store. And computation. Can you force a computation in either a built-in function or some operator that shouldn't take place? Now, input and output constraints are easy to do from a black box point of view. You don't need the source code to wank on the system until you eventually get it to break. If you have the source code, stored data and computation constraints are much easier to find, although sometimes you get lucky. Just based on your knowledge of how you might have written the software, you can break it that way. But if you have the source code, you look through it for data structures, and each one, you try to underflow it, you try to overflow it, you try to get it to store bad data. Computation, you look for operators and built-in functions, and you try to give them invalid operands, try to give them invalid data, or force them to produce a result that shouldn't or couldn't be stored by the system. So simple. Now, in order to make sure you understand these four, I'm going to show you four more bugs, one of each, and there's still stuff to be learned from each of these bugs. I tried to get the most interesting ones I could, and I made a special effort to make sure they were all Microsoft products. WordPad. This is an input constraint. So what I do, actually we built a little tool to do this for us. I'm going to demonstrate that tool at the end of the talk. To go and find the places where inputs enter into the system, and then using various tricky strings that we've come up with, try to break it. So what I'm going to do here is I'm going to go to the Format menu, Paragraph Dialog, and that gives me a nice little place where inputs come into the system. And I'm going to give it an illegal value just to figure out what's going on here. So in the indentation, I put 1,234. And it tells me, it constrained the input. It tells me the measurement must be between negative 22 and positive 22. Now, remember that value, because it's going to change. And as soon as you see those numbers, as soon as a tester sees those numbers, you see, aha, I got boundary conditions. Now, a tester is trained. By training, a tester should execute negative 23, negative 22, negative 21, negative 1, 0, 1, 21, 22, and 23 as the boundary conditions for that value. Now, that doesn't work, because I'm going to show you some boundary conditions for this dialog box that no reasonable methodology would ever have come up with. But testers aren't reasonable people, so we find these sorts of things anyhow. So let's click OK. You want 22? How about a 17-digit number? Oops, it took it. So that 17-digit number must have been between negative 22 and positive 22, right? Now, we broke the constraint. The tester's sitting behind the keyboard smiling. It's just a matter of time until this software dies. So let's experiment again. It took 17. All right, let's try a 65 length digit. I told you it's going to change. Now all of a sudden the measurement has to be between 0.04, it won't take negative numbers anymore, and 22. What have we done? It's storing negative 22 and positive 22 as variable values. And we've changed those values by inputs to the system. This is a tester's dream. This is why we love our job. This software is ours. It's just a matter of time until we bring it to its knees. We've got it completely confused. It's in a state that it's absolutely not responsible for its actions at this point. Okay, so 65 doesn't work. How about 70? That's called a buffer overrun. And so now we've got a serious bug in this software. By the way, a character string of length 130 just makes the application disappear. you don't get an error message at all. So this is nice, and this was hard to find. Our automation found this for us. As soon as we found a student brought this to me. By the way, in order to report a bug in my class, it has to be reproducible, and it has to end in either some sort of data loss, data corruption, get Word to drop a paragraph sort of thing, or an actual crash. I don't want to send this to Microsoft or any of the other sponsors and have them come back and say, that's not a bug. Testers don't like to hear that. And so he found the negative, he found the 0.04 to 22 thing, and he couldn't reproduce it. So we knew there was a bug in there, so we wrote a little monkey that just went in there and tried all kinds of different length strings until we finally reproduced it. And that monkey became a tool, ICBM, Input Constraint Breaking Monkey, that I'm going to demo later on in the talk. Was there a hand over here?
But if you start from the biggest number, would you get the same result?
Yes. Well, no, you need to corrupt state. You need to corrupt state before you get to this point. If you start with 130, I believe you get the same result, but I'm not sure about 70. I don't think so. But you can feel free to try this out at home. Okay, so those are input constraint bugs. Are there any questions about input constraint bugs? They're fairly easy to find in software. They're harder to reproduce, and that's why we need tools to help us with the reproduction problem. Okay, so let's go to output constraint. Output constraints are a little bit harder. Output constraints, you have to sort of have some domain expertise. You have to know what invalid outputs are going to be, and then you have to attack the software from the input domain in order to force that behavior. So that's kind of difficult to do, but it requires some domain expertise. So here's a little calendar. What's an illegal output of a calendar? Well, how about leap year February 29th on a non-leap year? February 29th, 2001. Can we force that? Well, if we go directly to 2001, February only has 28 days, so there's nothing to select. So let's try to trick it. Let's go first to year 2000, which does have, and February, which does have 29 days, and let's select that. Now we've told the calculator explicitly this is the day. Now how about if we change the year? Going through the back door, 2001, 2002, we've effectively added a day to every non-leap year of the calendar. So you guys have more time to test now. You got a lot more days to test your software. This is a Y2K bug that Windows NT has fixed. And I showed it to the Windows NT people yesterday, and they said, "Oh, that's embarrassing. You have an old service pack." And I said, "I have all the service packs." we keep machines with all the old service packs just to compare the bugs from one version to another. It's well known that developers fix bugs and create new ones when they fix the old ones, and so it's like giving us new toys to play with. So those are output constraints. Those are much more difficult to find than input constraints, and we haven't figured out how to build a tool yet to do this. It simply takes too much domain expertise, and so manual testers who you have to know the leap year rule in order to be able to find this bug. If you don't know what a leap year is, you'd miss this. This would look like valid behavior to you. Now, okay, so they fixed this bug in Windows NT, but this little application still behaves this way. But Windows NT will not allow an invalid date. They fixed that bug. So what happens if I hit apply here? What would be a reasonable behavior? Maybe change the date to February 28th? I mean, I told it. I wanted that the year is 2002. I explicitly told it that. Well, let's see what a reasonable behavior is. How about if we just backtrack to the last historically accurate February 29th? Well, that's what they did. They changed the year on me. So, I don't want to argue. That could be reasonable behavior from their point of view, but it seems sort of odd to me. Okay, data constraint bugs. This is a nice one. I've got a formula stored on the clipboard for Excel that it's not going to like. I'm going to paste it in here. And this is a long formula. There ain't no doubt about it. Now, our little monkey went through here and found the exact place at which you get this dialog. One character less, you don't get it. One character more, you do get it. And all those characters. And so we isolated this. Formula is too long. That's wonderful. Excel does not have an input constraint bug. It's got a different one. It's funny. The developer knew they shouldn't have stored this bug, and they did it anyhow. It's in there because I can now go to 1A and do anything. I hit enter, and I get another buffer overrun. So the input constraint kicked in. Don't store this. This formula is too long, and it stored it anyhow. And I exploited it. So that's a data constraint problem. Now, they're even harder to find. Data constraint problems, you really do need the source code in order to be good at finding them, in order to find them quickly and efficiently. Otherwise, it's hard to find out where the data is. You have to do it from a black box point of view, and you can eventually do it. We don't have the source code to Excel. We found this one by accident. This is one of the homework problems that a student, Luis Rivera, turned in for his first assignment. So those are data constraint bugs. And now let's do a computation constraint bug. This is Microsoft Money. If we want to do computation, why not go after something that computes a lot? Uh-oh, we have money people in the... Oh, okay. What we're going to do here, I'm going to create a new credit card account, and I'm going to put $999 billion in it as my credit limit, and then I'm going to make some charges less than that, some reasonable charges that are under my credit limit. So I'm not going to violate any rules of the application. I put a lot of money in, but I'm charging less than that. There, see, there's my account. I did that one for Bill, just in case he's watching. So I got an account. I got a lot of money in there. And now what I'm going to do is I'm going to make some charges. I'm not going to do anything wrong. So let's go through here and click next, and let's go shopping. We got a credit limit. This is America. And now you're going to see a couple of output bugs along the way because of that big number, but you don't really need a big number to reproduce this. There you go. That's not much. That's $100 million. I think it's $100 million or something like that. So now I'm in debt. This is America. There's an output bug. See those overflow numbers? Now I'm going to say, okay, I got to get out of debt. There's another output bug. See those overflow numbers? Got to get out of debt. Alan Greenspan would appreciate me spending some money. And I'm going to say, I want to get out of debt. That's a lot of money I owe, $100 million. It's going to take me a while to pay it off. I can't pay it off any earlier than the year 2027. And so now I'm going to tell money to show me how fast I'm getting out of debt. Show me the curve, show me my account, give me some information about how fast I'm getting out of debt. Remember that number, 2027. That's when I want to get out of debt. But money decides I'm richer than that. Anybody with a credit limit like that can pay it off in the year 2006. So it miscalculated. It miscalculated the answer. And I know it's not an output bug. I know it really stored it because I can go here and I can view my schedule chart by account. And once again, there's the date. December the 5th, 2006, even though I asked explicitly for the year 2027. So I was able to trick it into computing an incorrect value. Now, once again, this is hard to do from a black box point of view. This was also turned in by a student, Florence Monte, who was using this, balancing her checkbook, and so she naturally used this as her homework assignment, and she broke it. So this is an example of a computation bug, and again, give me the source code, and I can find these things a lot faster. Okay, so how can we generalize this? What's really going on with software? And now that we understand why software fails, and I can teach novice testers, I can show novice testers this theory and make them very effective bug finders, extremely effective bug finders. Within minutes, they can bring software, thoroughly tested software systems down. What's really going on here? And how can we describe these bugs, and what's our research agenda concerning this? So I'm going to talk about, get a little bit deeper into why these applications are failing, and talk about some technology and some tools that we can apply in order to write better software, be better bug finders. Am I doing okay on time? Okay. This is software. This presentation was not made by art students. This big blue circle in the middle is software. Now, we've discovered that there are only 4 types of interfaces that software can have. And we can break software from any of those 4 types of interfaces. Those interfaces are human, software, device, and document. Again, I'm willing to entertain that there might be more, but I haven't found any yet. All the software we've been able to test falls into one of these categories. So let's look at each of these. The human interface are things like command line interface, menu-driven interfaces, GUIs, and any place that a human, any apparatus for a human to communicate with a software. So that's a web interface. We have graphical user interfaces, and we have command line interfaces. Those are all ways for humans to communicate with software. And so the problems at testing here are coming up with all the inputs to apply over this transition and figuring out what all the valid and invalid outputs might be that the software is actually capable of computing. So we can apply our technique there. At that interface, we can go through input, output, data, and computation constraints. The next interface that's interesting is a document interface, and this is one that's largely ignored. And we've got a really nice bug in Word because of this. A student of mine is writing their PhD dissertation. And every time Word loaded the dissertation, it crashed. There was something in that file that Word didn't like. There's a field, there's a value out of some range that they weren't processing. Those are inputs. And as testers, we largely ignore the file structure when we're testing. We don't go through a lot of variations of what that binary could look like and test all those possibilities. And certainly the developers trust the files. They read the files without a whole lot of error checking. And so there's a lot of bugs there at that interface. And so we've got this nice little file. You click on it and Word falls apart. By the way, that student wrote his dissertation in LaTeX. And so we also have the interaction between users. Now, this is a really tough testing problem because the software doesn't have any control over this interface. See, we've got humans and documents talking to each other outside of our control. So the situation might be something like this. We might have a document opened in a word processor, and someone goes on the outside and renames that document. We don't have any control over that. Or we might have another file open down here that actually gets deleted from the operating system while we have it open. So see, we've got users interacting outside the software system, outside of our control. We can't constrain them, but we've got to be able to work with what they've done. All of a sudden we save a file that's no longer there, or we save a file that's read-only that used to be read-write. We've got a problem. And that's another interface for testers to pursue. And another one that's largely not pursued, and some of the bugs we're finding are based on those types of situations. By the way, Word handles this quite well. What are the other interfaces that we have to deal with software? How about software interfaces? All software has software interfaces because all software executes on an operating system. All software has to allocate memory and save files and things like that. And when they do that, they go through an API to the operating system. Well, again, this is an interface that software developers trust. You allocate memory. What's the next thing you do? You keep executing. You don't check to make sure that you got what you wanted. Did you get enough memory? Did you get any memory at all? We're going to show you a tool a little bit later that disrupts that communication between an API and a software system. And we're going to show you how poorly software handles it. So this is another one of those interfaces that is trusted and that isn't tested well enough in the laboratory. So we've got all of these APIs that have to be tested. We have to be able to make these calls and vary the parameters and make sure that the software systems work under those. And we can apply our technique at that. Input constraints, output constraints, data constraints, and computation constraints. There's only one more interface I've been able to find. If you write a device driver, you have to read protocol. And so the device interface is the fourth interface. And so now you're reading packets off of a wire. You're reading ARP packets, RIP packets, TCP packets, ATM packets, whatever they happen to be, and you have to process those. Those protocol streams have fields. Those fields have values. Those values can be valid. They can be invalid, in range, out of range. They can cause data to be stored. They can be corrupted, and we can apply our methodology at that interface as well. Now, we haven't been able to find any other interfaces. Some of these interfaces have things in common. The fields of an API are a lot like the values of a parameter in an API call, which are a lot like a text box input field for a GUI. So the techniques that you actually apply and reason with can be the same. Now, the problem is still not over, because inside this, the only thing that exists outside the software are inputs and outputs. What exists inside the software are states. The first thing that exists inside the software is data. And here's a little program I wrote. It's got a bug in it. It's an embarrassing bug because I wrote it. And again, I wrote this in my development class, and we found the bug in my testing class. When I told my students, go out and break published code, I didn't mean my code. So next time I teach that class, I'm going to be more explicit. This little program has a bug in it. The array, this is an expandable, collapsible array. It's a little Visual Basic example I use to teach students how to build an abstract data type. And so the array, once it's been expanded, you see it expanding here when it needs room. Once it's been expanded, it can be underflowed. And so we have to consider the actual data that's being stored underneath in order to be able to figure out how to break software. And so this poor thing can be underflowed. The other thing that we do inside software is we compute. And here's a little pseudocode fragment that also has a bug in it. Now, this was the original program that I found the bug in that led to all of this. This is a little running average example. It doesn't get any simpler than this. I actually got this out of a book originally called Zero Defect Programming. And they had it, and I thought it was funny at the time because they weren't filtering inputs. They were trusting that every input was a non-negative integer. And I thought, there's a bug. Hey, there's a bug. And so I built this little case statement around the input to make sure that I only computed with things that were really non-negative integers. Can you see the bug in this program? You all are researchers, not testers. There's a glaring hole in this program that's at the same time very, very subtle.
All through?
I'm sorry?
Is it all through on the case non-negative integer?
No, that's too easy. But yeah, you're right. There's not an otherwise statement. Yes?
Is there an overflow?
You got it. Very good. So there are some testers in the group. Current input, when you get an input, let's say this is a 2-byte integer just to make it easy. So let's give it 65,767. Is that right? 32,000. Yeah, right. 2-byte integer, something like that. Whatever the maximum 2-byte integer is. And then when we fall through here, we get the sum is equal to sum plus the current input. So sum becomes the maximum integer. Next time through, down here, give it 1. You can give it the maximum integer again if you'd like, but 1 will overflow sum just as nicely. So we have to worry about computation. Now, are there any developers in the group? How do you fix this? Exceptions won't work. Change the contract. The way we'd fix this is we'd have to have an if statement here that said if maximum integer minus sum is greater than the current input, then we can make the computation. Otherwise, we can't. So we need to be able to filter this computation one step further. Now, unfortunately, the development side of this, the solutions to this problem aren't quite as nice. We have to put if statements in our code. We have to wrap our data structures. We have to not write code in C. We have to do all kinds of things that will keep our software working. C is problematic. Give me a C program and we can break it. If they do 3 things at least wrong. Pointers, floating point numbers, and dates are extremely buggy in C. So, but that doesn't mean C is bad. C was bad long before I made that observation. All the programming languages have their problems. So it's not just C. We can break Visual Basic. We can break Ada. We can break Perl. We can break Java. Okay, so whoops, I didn't mean to do that. bear with me for just a second. I'm going to demo my tools, and then we're going to stop. I'm going to have to go through this just a brief second. So we have the data constraints. We have the computation constraints. And when we get back, the real solution to this is to make software state aware. We built a program at Florida Tech. We built it's a small, simple application, but we made it state aware. We added some data to the program, just one or two variables that kept the software within its bounds, that kept the software within its state space. And we have not been able to break that piece of software. No matter what we do, no matter how we bug it, we find the bugs. So we can insert any bug you want, apply our technique, and the bug is exposed. So we think the concept of states as an additional piece of data to keep your program working within its proper space is important. Because what happens is that software falls outside of its state space. We really have the software that was intended to be written and the software that was really written that looks like this. We have this intersection. So let's picture one of these circles as being the software that you wanted to write. And if you wrote that software with that state space, it would be correct. And the other circle is the software that the developers actually wrote. You end up with three different state spaces. You end up with the correctly implemented states. I told you, we're not art students. The color coordination is lousy. That's why we dress like this, too. These are the correctly implemented states. And as long as the software stays within this state space, it's going to work just fine. There's another set of states that I'm not all that interested in, which are the states, and ignore our grammar, too. The states that are not implemented. Now these, Microsoft testers are very good at finding. When we get the software, when we get retail applications, all the functions and features are there. It's very rare that you forget to implement something. These states over here are very interesting. These states over here are the ones that the software will go into, but it shouldn't go into. And these are the states that we're looking for in our research. As soon as we get on this boundary right here, as soon as we get software at that boundary and are able to gently shove it over into these orange states, that software is ours. It will eventually fail. And so I think this is a nice intuitive picture of what we're doing. We're trying to push the software to that edge and then nudge it over. And once it corrupts states, there's hardly any way of getting back. It's eventually going to die. And those are the dangerous states, and those are the ones we're working for. When we're testing over here, we call this destructive testing. When we're testing over here, we call this constructive testing, because we're actually trying to make the software do legitimate things. And destructive testing, that's where security testing and things like that lie. You want to try to do really nasty things on purpose in order to find buffer overruns and get into your hostile users. So this is the picture of software that we painted based on our study of all of these failures. And this is the picture that we're working with in order to build tools that push software over here. So now I'm going to demo some of those tools. But I want to summarize just briefly by saying these are the important things that we've found. We have to worry about the environment, because inputs don't just come from humans. Inputs come from software, devices, and documents, and we have to be able to simulate and mess around with that environment. We have to worry about which input values we select and which input combinations. We have to think about outputs and how they can be generated. We have to worry about data structures and try to get them to store data they shouldn't store, try to underflow and overflow them. We have to worry about computation, and then again, states. States is the newest concept here. And the concept that we're working on in order to try to develop correct programs, in order to make perhaps the world's first correct software program. Now, tools need to be built at each of these stages, because this is very difficult to apply as manual testers. And so we've got 3 tools so far. I'm only going to have time probably to demo 2 of them. I only have 4 minutes left. So let me just briefly describe each. Heat stands for Hostile Environment Application Tester, and HEAT tests API interfaces. It sits between, and currently it sits between an application and the operating system. And it intercepts calls to kernel 32, GDI, and user 32, and returns back values that we decide. So you allocate memory, and we might decide, no, can't have any. You might try to save a file, and we decide, no, not going to allow you to do that. And we watch how the applications don't handle it. And I'm going to demo that tool for you. ICBM stands for Intercontinental Ballistic Missile, right? When you want to fight a war, but you don't want any of your people to die, you sit back and you launch an intercontinental ballistic missile, right? And it goes over there and it does its job, and you're sitting back in your living room nice and comfortable. Well, our ICBM stands for Input Constraint Breaking Monkey, and it's the same sort of thing. For no cost, there's no setup whatsoever. You toss ICBM at your application, it goes through and finds places that inputs enter the system, and it pounds on them. And so your testers don't get bloody and dirty, and they can sit at home in their living room. SPCS is our state generation engine. We're trying to, obviously, the Achilles heel of the state theory is that there are too many states. And so this is a little artificial intelligence algorithm that generates state spaces from specification of states. And so I'm going to demonstrate HEAT first. I'm going to test Word with HEAT. Right now, I've only got Word and Excel. What we do is we go in and we read the header, find out what DLLs you're accessing, and we step in front of those DLLs. So I understand there's a similar product in Microsoft Research called SWORD, and something else called Detours that's publicly available that does similar things. We intend to give HEAT a great deal of control, and what we'd like to do is select the exact place at which we cause those failures. Failing software at the operating system interface, you might argue isn't fair. But if you fail it at the right location, and we can determine what those right locations are, then we can simulate, congested networks. We can simulate real-world scenarios. So don't be too hard on this product, although it is pretty nasty. So let's go to Word. And so here's in this demo, I only can block these 6 APIs, but right now I think we've pretty much got all of kernel 32 taken care of, and we're working on user 32 and GDI. We'll go after MFC. We'll go after database libraries. We found a bug. We diagnosed an Outlook bug using this tool. There's a problem between the database and Outlook that we were able to intercept. But essentially, it's flexible. It can stand between any software interface. And so we can block any of those. But let's not do that yet. Let's just show you that Word really works, even though we've modified its header. Word's looking at kernel 23 right now. That's what we call our kernel. So, look, it's working. You can open files, you can save files. Haven't changed Word. Haven't changed its behavior anyhow. We're not touching the program space, at least not yet. We have some ideas about that. Now, let's block these. This means Word, whatever will happen, whatever call Word makes next, we will pass back a randomly selected valid response from the operating system, but one that Word's not expecting. So we won't just fail it. We'll select how to fail it. And there are various options. Although it's funny, whenever you fail the save file, Word always assumes that it's, it either immediately crashes or it catches it and assumes that the disk is full. It's like that's the only thing the developer could think of. If this doesn't work, the only thing that could be is disk is full. And so let's go back over here to Word, and let's type some text and save it. Ouch. It didn't handle it at all. So it crashed immediately. It didn't have access. Kernel 23 denied it access to the write file. And so it crashed. Now, we've tested Word and Excel extensively with HEAT. Would you like to know who won? In general, Word has been more robust. Its operating system interface has been more robust. One of the interesting things you can do is you can give it back memory. If I go back over there to the HEAT window, I can unselect that. And in real time, I've allowed those memory calls to work. Word is, so far, the most patient software system we've tested. It'll try sometimes. Not all time, obviously. But sometimes it'll try, and then when you free memory back up again, the operation will work. So what I'd like to do now is I'd like to do a test. What is the most robust operating system word processor out there? Test them all. What's the most robust spreadsheet out there? Test them all and see who's doing the best. So that's heat. Oh, this is nice. WinWord's still running. Crash, but process. This is fairly common. No surprise here if you've done any testing. Applications crash fairly often, and they're still resident in memory. Still think they're running. Okay, so now let's go back and test. I'll show you. I'm already a minute over, but if you'd like to stay for ICBM, I'm going to show this. ICBM, again, input constraint breaking monkey, and I'm going to test WordPad. You can test anything with this. What you do is you go up here and you click Get Windows. And it goes out and finds all the active processes on your machine. And then you come down here. So this right here, this middle one are all the active processes, and these are the classes that you can select that it could identify from those processes. So now you come down here and you find. I found the document. Okay, so that's my WordPad process, and I'm going to test this WordPad class here. So I could select any of those I wanted. And now in order to save time, I'm not going to go through, but what you can do is you can program this thing to go through as many levels of menus as you want, and it'll go across all the menus, and it'll find the menus, and it'll find dialogues, and if it detects a control that it recognizes that will take input, it'll log it down here at the bottom of the screen. Oops, I forget there are two screens. It'll log it down here in this client area at the bottom of the screen, and then you select down there which inputs you want it to test. And then right here in this section, these are our test libraries. You can open new test cases. You can type in new test cases on the run and save them here by clicking that little disk. And you can use various libraries. One of our big areas of research is coming up with the right strings to test and the right string generators to test. It's a hard problem. And if we come up with better strings, we're going to find better bugs. So let's go down here and then go to the current level of 1. I'm going to filter this a little bit. I'm not going to go through all of the menus. Instead, I'm just going to go to that format menu, which is my friend here. And so I start and end with Alt-O. And then I'm only going to go through, for the second level of Windows, I'm going to say Get Available States. States is the wrong word. It's not. It should say Get Available Input Entries or something like that. And I'm going to go through and I'm going to find these. And now I register this window and I try test cases. So I've registered that window. So you see down here at the bottom I've got Alt-O plus P. Now if I had done this for the entire application, I'd have a whole string of places where inputs can enter into this system. I had dozens of them. And then I could just go through and select one or more of those, and it'll go about its business and test it. And you also see this little entry place here that said path to the program in case of a crash. If we do crash it, you enter the executable there, wordpad.exe, with the right path, and ICBM will relaunch it and continue testing. So let's try those numbers. It says try test cases, and bang, bang, bang. Now it's going through combinations. It's clicking buttons, and it died. That was 130 length string that you saw there. WordPad just completely fell apart on 130 length string. And we have a problemo, a guy who wrote this from Argentina. And it says, can't get back. This is our error message that says we can't find WordPad. It's gone. And so ICBM and Heat are both in the prototype stage, and we're still doing a lot of work on both of those applications. But now we're at the point now where I have developers on both of these applications, and I have testers who do nothing but sit with Heat and break stuff. Do nothing but sit with ICBM and break stuff, and so it works out. It works out quite well. Okay, so I won't keep you any longer than that. SPCS is another application. All it does is generate states. The demo is not that interesting. Now, what we're doing at Florida Tech in order to trial run this is we test real software in our lab. We get sponsors to give us products, and we apply these tools, and we test these products, and we build test automation. We think it's important that we work with real software, and not just toy academic examples. And the temptation to work with toy examples is so hard to deny, but we've been able to get past that. And so if you have applications that you're interested in having as tests, let me know, and we'll turn up the heat and launch a couple of missiles at them for you. That's all I have. Are there any questions? Thank you.